Okay, folks, if we could go ahead and grab our last little bits of drink and come over, we're going to go ahead and start. First thing I want to say is I want to welcome everyone here to the San Francisco Java User Group and to Pivotal. Is this anybody's first time at Pivotal? Welcome. A little bit of housekeeping. It is not your first time here. A little bit of housekeeping. Bathrooms are directly behind this wall. It is easier if you go down the hallway over here. We do have, there's pizza. I presume most people have found that. And there are some other beverages and things over in the kitchen area. We do ask that people not consume alcohol because we don't have a license for it. Is everybody here, anyone not familiar with Pivotal? Okay. So Pivotal's done a lot of work with open source. Anyone here ever used Apache Geode? Or Apache Tomcat? Or Spring? So a few little known facts. We are, of course, the maintainers for Spring. That is generally known. Something around 75% of the lifetime commits for Tomcat were made by Pivotal employees. We also we have a couple products, a platform as a service cloud called Cloud Foundry. And that is written here. We sell that. It allows, kind of abstracts away infrastructure to allow your application development teams to move at a higher velocity without having to worry about things like databases and all these details for things that they generally don't care about. We also have a services arm, which is where I work, where we offer various types of assistance for clients to implement and either use that particular cloud or labs. The specific organization I work in will work alongside enterprise clients to develop a product and to teach more agile practices, including XP and TDD. So that's kind of a 10-second intro into Pivotal. To build on top of TDD, Julien is actually a client engineer with us. He's been working with us for 8 months now? 8 months. 8 months now. So he's been here for a little while and has actually a lot of expertise in TDD and is going to talk to us about some things that we can do on top of our traditional testing for TDD to give us more confidence. So without further ado, I will let you take it away.
Thank you, Bob. And I'm very honored to be here. Thanks, Java User Group, for this possibility. Thanks, Pivotal, for hosting that. We're going to talk about a little bit about correctness today. And when we say the word beyond TDD, obviously we don't mean to disregard TDD as something that's not necessary. It's about expanding our design principles to take it even further towards the idea of correctness. A little bit about me. Name's Julien. That's my Twitter handle. I work for Goldman Sachs. Specialize in fintech, credit card, consumer finance, mostly because this particular domain of tech is very impactful on people's lives and has a potential to change the behavior for better. So let's start. Let's look at this simple program. It's written in a made-up language, but the way it's structured kind of clearly tells you what it's supposed to do. So let's ask ourselves a question. Is this program correct intuitively? So hands up who thinks this program is correct? All right, kind of, yeah. Hands up who thinks this program is not correct? Yeah, I wonder what the other folks are thinking. Or maybe hands up who thinks it's not possible to tell. Nice. So, in fact, it is not possible to tell. And the reason for that is we don't know what is accepted as an input, what validations are we supposed to perform. There is no proof of correctness that we can come up with to tell about that function. And we can also say that in this case, it's a division, so there could be a division by zero problem. The arguments that are passed could not even be numeric values. Who knows? So how do we come up with proofs? It's either by manual verification, so we can just run a function, which is a program. Or we can write a unit test. That's hopefully what most of us are doing. Or we can go even further and take a mathematician's approach and come up with a theory that is mathematically provable by means of induction. Or in such a way that if we try to prove the opposite, it leads to contradiction. Here's another program, or rather a diagram that represents some idea of an enterprise program. And now if I asked you, is this correct? What would you say? Probably no. You wouldn't even think, what is this about? And the reason for that is that we only know, the only fact we know about that is there's a very complicated graph of dependency, probably infinite number of states that this system can be in. And so it's complex enough so that it's not possible to describe it completely. In fact, I used to work on a trade surveillance system that was fairly simple in terms of it was processing a very well-structured data. It didn't have any interactive way of communicating with the user, and still the specification for this system was 160 pages, and it was pretty simple system. So whenever you add some interactivity into it, it's basically becomes too complex to describe. Now, so let's now move on to regular languages. Start with JavaScript. I think we all know this language at least a little bit. So another question to the audience. Can someone attempt to tell me, what does this function signature tell us? What can you say about this function just by looking at this signature? Come again? Something is being appended. Okay, because we have a name, append. What else? What else can we say? We can say one more thing. It is a function. Oh, that's actually a third thing. We can say one more thing. It takes 2 arguments. That's right. So that's the extent of expressiveness of JavaScript. You cannot say anything else about it. Do you know of any language that is even less expressive than JavaScript? Do you know of any language that will not allow us to say that a function takes 2 arguments? Well, not talking about that low level. It's actually Bash. That's how you would define an append function in Bash. You have to take care of figuring out the arguments. But we're not here to talk about Bash. Now let's move a little bit further on the whole ladder of correctness. So the next one is Java. What can we say about this method? Anyone? Go ahead. It returns a list of certain type. Exactly. And then both arguments have the same type for the list. And we still know that there are 2 arguments. We don't lose that information, which is great because And now we don't have to, well, yeah, that's a good question. If we have a JavaScript function like that, what would we have to test for? Because we cannot express stuff in the code. So what would we have to test for? Yeah, we would have to test for argument types, because what if appends takes a null, or one is a list and one is a numeric value? How does it behave? Does it still yield a result, or does it error out? In terms of Java signature, it's granted to you by the virtue of type. You don't have to test for it. It's just there. So now tell me, because Java is not definitely on the peak of expressiveness. So tell me, what can go wrong here? Or what didn't we express? What would we need to test for? Nulls, right? Yeah, nulls, definitely. What else can this? What else is can this method do that is not presented here? How can it fail? Yeah, one of the lists could be modified. That's right. One of the the arguments are not safe in terms of mutation, so to say. It can also throw a runtime exception, right? In fact, one of the things it can happen is this function might never terminate. We don't know that. And of course, it can modify a shared global state that's not even expressed here anywhere. Come again? Yeah, exactly. Exactly. No, not at all. But I tried to come up with an example that is suggestive enough for us so that we wire ourselves to think of appending lists. But for that, we should test anyway. That's right. All right, we move to Kotlin. It looks kind of similar to Java, but we get one more guarantee. What is that? Null safety. Yeah. This code will fail compilation if there's any possibility of passing null to that. So that's why we like Kotlin. Exactly. All right. So do you think there's anything else we could add to the expressiveness of a language? Let's see. Let's try Haskell. It's a lot shorter syntax and yet more expressive. So maybe let's go back to Kotlin. What can go wrong here of the things we haven't yet mentioned? Apart from the fact that this might not terminate, for example. Come again? Yeah, it can mutate a global state. It can, in fact, mutating a global state is one example of a general concept of side effects. So that's what Haskell gives us. Haskell guarantees that there will be no side effects if you're looking at a function that has a signature like that. You would have to use special constructs in order to design explicitly side effects. And that's a tremendous expressiveness of a language. And until recently, I myself thought that you can't go any better than that. Until one of my friends here at Pivotal told me about Idris, which is a language from a family called automatic theorem provers or something like that. It's apparently a type of languages that mathematicians use to help them prove theories in an automated way. And Idris is built on top of Haskell. The thing you can see here is that it can guarantee you in the type declaration that the resulting vector would, the size of a resulting vector will be the size of the sums of two input vectors, which is a nice thing. But the other thing that Idris guarantees that you don't see here actually is that it will guarantee you this function will always terminate. It has a built-in check for that. This family of programming languages is called dependent type languages, and there's a bunch of them. There's Agda, there's F star, there's Idris, and a couple of others. And here we're kind of hitting the limits of expressiveness of languages. It's I don't know any higher level of expressiveness that you can achieve. So whatever else we don't know yet about this function, we would probably want to express through unit tests. And yeah, so a question, if we really had an even more expressive language enough to communicate all program requirements, what would that mean? We probably would not need tests, but we probably would also not need software developers because we could have a program that automatically writes whatever agrees with the specification. And we would be in a situation where a specification actually becomes a programming language. This is a pyramid of wrong. And we won't be talking about wrong ideas. The concepts of types and tests reside somewhere behind wrong code and wrong specification, particularly at the boundary. Now, what is really a test? Test is kind of a control system that keeps the program and the programmer honest. So it proves that the program represents the specification properly. But the question is, can we do better? And, whoa, this slide got a little bit big. Anyway, so that's a quote from Alan Turing, and that's like 1/3 of Alan Turing's face. Sorry for that. Yeah, I hope you do. So he says, with a digital computer, we can no longer rely on common sense, and the bounds of error must be based on some provider inequalities. We need analysts to find the appropriate inequalities for us. We are these analysts, and this guy is talking about, specifically in mathematical terms, inequalities, but in type system terms, it's any type of constraint, really. So it's the act of constraining the system in a proper way is what is the most important consideration for us. But sometimes it takes someone to express the known idea in the simplest possible way to kind of, for the simple minds like mine, to latch on. And that's my favorite from Yaron Minsky, which is when you code, make illegal states unrepresentable. That's from one of his lectures. And that's a slide from the Hollywood movie Hackers. It's from the 90s. And clearly someone did not make illegal states unrepresentable here. 980, yeah. So, and the last quote, I promise, is from Max Alexander, is where he said in his book, Understanding Software, the world of computers is full of things that should have been strict from the beginning and became ridiculously complex because they weren't. And that I give you that quote because it's emphasizes this problem that lack of proper constraints lead to complexity, which is very hard to get rid of once established. So, and we all talk about refactoring and to some extent fool ourselves that it's always possible to restructure the code to our needs. But the fact is that there are certain seeds of complexity at the very early stage of design that when they grow, it's almost impossible to eliminate them. Because any refactoring that you do will be either very shallow, so yeah, I'm going to do null checks or whatever, but you cannot redesign the entire system because someone decided to use a certain type that should not be used. And so it's either very shallow refactoring that's possible or very expensive. That it's very hard to get a buy-in from the organization to do it. And I want to maybe, why is it even important? Why am I talking about that? And I'll actually read that up because I don't want to lose my train of thought, and it's probably the most important message I wanted to convey during this presentation. Is there are two forces that suppress progress in our industry. One is pointless attachment to the old ways that prevents new ideas from emerging. And the other one is similarly pointless chase for new ideas without any rigor about validating their usefulness. The problem is that there is no one who will keep us as software engineers accountable of our ideas but ourselves. Because to the rest of the world, programming is an esoteric discipline of talking to a machine. So we can either take the easy way, jump on one of the bandwagons and have a pleasant life, or we can follow in the footsteps of the founders of this discipline and become mathematicians, or strive to become mathematicians, as Alan Turing liked to put it. We all have certain intuitions, but we need to strive for evidence. When we talk about test-driven development, why is it good? I've been in a situation when I had to explain to a CTO why we want to do test-driven development and get a buy-in to actually be allowed to do so. And it was not very long ago where I had to explain why having a continuous integration server is actually better than having a team of people on the other side of the globe manually compiling your software. So it still happens. So we would have to look for formality, for proofs of what we think is right. Otherwise, we are no better than this guy who sells snake oil, having clients and employers pay us ridiculous money for something that does not improve their businesses, that has no value added, and when aggregated leads to wealth destruction and suppression of progress. Okay, enough of philosophies. A little bit of a summary of the spectrum of correctness that we have identified. And we can see that there is like a constant way forward right here. But one of the things that I want to note is, first of all, what we cannot express in a language, we need to express in tests. And the second of all is what the language is missing. You can usually make up with the tools. And Java is a terrific ecosystem that actually has a lot of tools that can compensate for certain lag in terms of design of its core syntax. which is slowly catching up, and I hope at some point we will have pattern matching in Java and immutable collections and goodies like that. And similar, even for Haskell, Haskell is missing with respect to theorem provers of type-dependent languages, but it does have a library that can handle things like that with kind of annotations, so to say, which is called Liquid Haskell. All right, so there's a decision to make. If you want to be super correct, quit and become an Agda programmer, good luck. You can also convince your organization to use a better language. Some of us are in the fortunate position to do so. Others are not. This is Java user group. We want to focus on technical things, not the organization things. So let's focus on the design, the tests, and the tools. And the first rule is that we need to start using what we have, because otherwise we don't have the right to even ask for more. And I get, for the sake of the arguments, let's say we're using a reasonably typed language like Java or C++, and I hear those languages take a lot of heat because of the lack of expressiveness, what they're lacking, and some arguments come from people who write code like that. And then they say, oh, I want to code in Haskell or whatever. And that's, yeah, a valid point, but the language itself will not solve your problems. If we don't understand how to properly constrain your code, even with the simpler tools we have. And so I'm staying by Java right now, specifically. But in most of the mainstream languages, for everything that you type as a string, there's probably a type already suitable for that. So don't use dates, don't represent dates as string. Use datetime, or like, please don't put JSON payload in strings in your codes. This is a very bad thing to do. And we'll define what does it mean it's bad in a second, because what I told you, we have intuitions, but let's look for proofs. Every type is a set, because we're working with computers which have limited memory, so obviously types also have limited amount of states or objects of certain type. For example, integer has 2 to the power of 32 states that it can have. Now, if you represent a month of a year as an integer, you would have 12 valid states and 2 to the power of 32 minus 12 invalid states, which means that those invalid states need to be tested for. Good luck again. And then, but you can also use the enum, which is a month, which a lot of libraries have. Java Times specifically, which is a core library, so you don't even need libraries, which has 12 legal states and 0 illegal states. There is it? Oh yeah, that's another thing. In Java world, every type is not actually itself. It's a union of null and the type. And that's something that's very frustrating, and that's why we all love Kotlin. Maybe in a couple of years, who knows, we will not have nulls in Java too. But let's work with what we got. Why is it good? Because we're making illegal states unrepresentable. But that's just like, that was a pretty boring type, right? So how about this? Big integer, which has infinite state. If we represent an index of some absurdly large collection as a big integer, we will have infinite legal states and infinite illegal states, because all the negative numbers will be illegal. There are some languages that treat negative indexes as like a backwards, but not Java. But we could use the type that represents a natural number, and that's natural number is very natural for an index. But that's just some value. So let's move on to something that's more interesting. A function. A function is also a type because it represents a mapping from one type to another. So it is a set. So it also has values. The number of possible values a function has is, in a simple function like a mapping from int to int, it's 2 to the power of 32 to the power of 2 to the power of 32. Now, if we wanted to write tests to prove absolute correctness of such a function, how many tests would you have to write? If assuming that one test calls the function once. Anyone? We would need to run the function for each of its input. That's it, which is 2 to the power of 32. And yeah, so this, what I wanted to say with this slide too, is that you can see that we've already observed that types can reduce the space of possible values and eliminate the entire subset of implementations that are invalid without us even have to write a single test. And we are slowly getting from an intuition to an actual definition, and so this is an idea from Julien Truffaut. I strongly suggest you to watch his presentation called Types versus Tests, which is a metric, a simple metric that's called valid implementation count. If you have a function that maps from type A to type B, and those notations are basically the size of types, then the size of this function is b to the power of a. Valid implementation count of a function is the total count of a function minus implementations invalidated by test. So if you put it in an equation, you would have this formula, which is b to the power of a minus n, where n is the number of tests. And let's enlarge it a little bit. What it means is that if we reduce the size of type A by half, we would have to write A over 2 unit tests less, or it will be equivalent of writing A over 2 unit tests. And so you see that reducing the size of an input has a certain equivalence in the number of tests we have to write in order to achieve full correctness. And from this, we can deduce that wide types, it is very difficult to deliver solid proofs of correctness only with tests. And that designing types is an activity that ideally should happen before the tests are even written. But unfortunately, function is a mapping only if we do functional programming. Because a regular function like that can have effects, and effects, they basically destroy everything. So let's see. What effects can such a function have? We already discussed that, so I won't be doing any more questions. Perform action can fail, throw a runtime exception. It can take a lot of time. In fact, it may never terminate. It can modify the input which is request, and it can modify some global state that we don't even know about. So how can we model explicitly those concepts? Let's start with throwing an exception or an error. There is a construct of try that multiple libraries in Java already have, which I'm not going to go into, like whether it's a monad or function or whatever, or functor or whatever. But the fact is that you can wrap your response in a try, and then its try can have one of the two implementations. We can either success or fail, and then you can inspect it in order to see whether it makes even sense to try to get a value out of that. So we're left with a function that will never throw an exception because the exception is represented by a return value. But it can also take time. Who can guess what would be the type that represents taking time? It's future. Future represents a computation that might still be ongoing, and we are expected to either wait for it indefinitely, explicitly, or define certain sane timeout in order to not to wait indefinitely and declare a failure. Now, it can still modify the input, of course. It can modify the global state. So let's represent an input as an immutable class, which then cannot be modified. And I know it's hard because even if an input is immutable, it can have a field that is a collection, and the collection might be mutable. So no one's saying it's easy in Java, but it's possible. And then it can modify global state, of course. So what you would want to do is probably inject all the dependencies into your system, into your piece of code as immutable dependencies. Now, so I want to, from this, I want to jump into this concept of that type is really a theory, that if we frame our function in a way that it's always returns something, because we modeled all the ways in which it can go wrong, we can call it a total function. And for total functions, you can develop theories. And theories, from those who took some maths, you have this either universal or existential qualifiers that says for all x, if y, then z. So if we go to our append to lists example, we can state that for any two lists, L1, L2, if the result of an output is appending, if the result is an output of appending L2 and L1, then the size of the result should be equal to the sum of the sizes of L1, L2. We can add more conditions after then, which is, for example, then L1 should be the front of the list and L2 should be behind it, and so on. And in fact, we do have tools in a Java ecosystem that allows us to define theories like that, of course, with sane bounds. This is an example from Quick Theories library, where I defined all lists of sizes between 0 and 100,000, and those are two lists. So we basically try all the combinations of those sizes, and you check whether the resulting size is always the sum of two sizes. And it took maybe 10 seconds to run this code. So obviously it's not a free ride, but you can actually manage to handle it with a proper library. And I'm not gonna, this talk is not about teaching you certain libraries or tools or design techniques. It's just to give you ideas of what is there so that you guys can research on your own. The genuine idea here is what is called type-driven development. I don't know who exactly coined this term first, but it's about what you can do before you even start test-driven development, which unfortunately is also abbreviated TDD. So you start with a type, you write a theory about that type, and write the code that implements this theory or a property. And if it does not hold, try narrowing the type, try refactoring your types. If you realize that you cannot narrow it down any further, start with test-driven development. How are we doing with time? Just want to be mindful. All right, I think I need to wrap up. So, 45 more minutes? Okay. Okay, then let's continue. Who wants to watch HBO Watchmen? Yeah, I'm waiting for that too. But this is more about a metaphor of who tests the tests. How do we test for the quality of tests? And there are actually tools for that. But first, let's ask ourselves a question. Why does test coverage threshold suck? Anyone wants to answer that? Oh, there's a microphone.
Oh, nobody wants to write test coverage.
Yeah. All right. So, wait, you said nobody wants to write?
Write testing code.
Oh, yeah. And in fact, it also leads to certain bad habits. Like if something is imposed on you, then you don't really care about it. You just like write whatever to meet this test coverage criteria. And here we have an example of our append function that has 100% coverage with 0% confidence. No, maybe 1% confidence. I don't know. So our tests are only as good as our assertions, right? And these are the most important parts of our system. So with helps comes mutation testing. So some of you might already have used it. Is that this idea is pretty simple, and there are pretty powerful tools around that. You have original program, and your framework, your mutation testing framework, injects a failure into your program and creates a mutant. Now, original program needs to pass for a mutation test to even make sense. Then you run your tests on the mutants. If the tests pass on the mutants, it means that you have not tested it properly, so it's a bad test. If the test fails, then we have a good test. And just to give you an idea of what is a mutation, this is a list of possible mutations from Java library called PyTests. But any language has at least one mutation testing library, so feel free to explore. You can change the conditions, you can change the increments, you can invert negative numbers, return nulls, change the switch statement, arithmetic operators. So literally, right now, the mutation testing landscape is so powerful that you can change your code in any way you want. And again, this means that you have to run your test multiple times, not once, because you don't want one mutant. You want probably hundreds of mutations and see how your tests perform in that. Which means that you need to write your tests in a way that they are executed fast. So never do thread.sleep, never log, never wait, never do any IO operation, even as trivial as writing or reading from a file. Please, this is not a unit test. And then a metric, because again, we already agreed to that test coverage sucks, and it just sucks a little bit less when you do PI testing. So an actual score an actual metric that is more driving your urge to actually fix something is a mutation score, which tells you, okay, I killed all the mutants. Then I'm happy. If you didn't, if you are told that you didn't kill enough mutants, the first thing you do is you want to fix those tests. Not necessarily so about 95 test coverage. So adding the mutation testing as a step to our recipe for great code: start with type, write a theory, write the code, try narrowing down types. If it's not possible, test-driven development, and then validate with mutation testing. And then do some static analysis, because static analysis always catches things that we were not able to catch otherwise. And remember, when we have a language that is lacking some features, there would usually be tools for that you should use. And then I have a quick section about but Java, because that's what I often tend to hear. It's like, but Java does not have some types, which means that I cannot write total functions. In fact, you can simulate a sealed trait, that's like the Scala's concept, by just declaring your base type abstract, and then declaring a private constructor so that you cannot construct any more types of these objects. You cannot subtype it anymore. And here you have a nice sealed type of either, which will allow you to do to use it to write total functions. But of course, Java does not have pattern matching, which is another really necessary concept in order for you to write to model your side effects in a proper way. But there are libraries to do it. I found two at least. There is Waver that has this nice construct of pattern matching by types, and there is Cyclops that have a little slightly different syntax that's a bit more alien to me. Maybe that's why it's called Cyclops. But still can be used and can detect problems at compile time. And then, yes, immutable collections. What can you do? Remember, immutable collection is something different than unmodifiable collection. But there are libraries, again, we have Pure4j, Guava, Waver, and Cyclops, those two other tools that are basically tools for functional programming in Java. They also have a bunch of immutable collections that implement all the goodies like memoization and efficient caching and so on. And then we don't have compile time null safety, and yeah, that sucks. And the best you can do is probably use the not null annotation, make sure you run find bugs. Probably in Eclipse, because you don't want to detect things like that when you commit the code and your build report comes back. So we reached the end of the presentation, and I hope I pumped your intuition well enough so the next time you'll be thinking about designing your systems, you will, first of all, will not use strings or any primitive types. And you would be thinking about how more can I constrain? What states are illegal right now that I can get rid of so that they're not representable, and use the tools that you have in your available for you with the language that you program with. And also share this with your friends who are in the same business. Any questions? I'd love to answer them now.
So there is one thing I would like to say, and then I'll take the question. Project Amber currently hosts a pattern matching specification for Java.
Project Amber.
Yet to be released, but it is in the works. So within the next couple of versions of Java, we will likely see pattern matching natively in the language itself.
Sorry, what are sum types? I don't know what that is. Sum types.
Sum type is it's also called sealed traits. Wait, where were we? No, wait, it was not that far. So if you have a type hierarchy of, let's say, a base type and a bunch of implementations of this type, then these implementations are called sum types, but the caveat is that you need to constrain this hierarchy so that no one else can implement more, can add more implementations to it. And that's why I gave either as an example, because either can only have left or right. It doesn't even make sense to have anything else. Similarly, optional. Optional is either some or none. Again, it's a sum type. And in order for you to constrain your function or constrain your system that you're designing, you need capability to do sum types so that you can write complete total functions. Yeah. Go ahead. Microphone.
I was a little bit confused by, so we make a type, and then we write code with that type, and then we do test-driven development after. Aren't we supposed to do the code after the test? I was a little confused by that.
Yeah, so there's no, let's say, it's almost like you have two layers. First, you work only with the names of types, and if they have methods or functions, they're signatures. No implementations. It's like if you programmed in C++, you just like write header files, let's say. In Java, implementation and declaration is actually tied together, so it's harder to reason about it, of course. But still, you could think of it like, how much can I guarantee by a type, given the type is the kind of specification that I'm writing? So you start with, let's say, interfaces, right? You start with interfaces. You don't need to test interfaces because you don't have implementations yet. You don't have anything to run. But you can represent certain dependencies, or you can represent certain possible states by just the virtue of having interfaces. So this is this step that is before the implementation. You don't really implement anything at the type level. Yeah. All right. Any more questions? Go ahead.
Yeah, I was curious about when you're talking about the generative testing, like where you could test all possible combinations of lists of like length 100,000 or something, right? That's obviously like very thorough and very correct, but you mentioned that that test took like 10 seconds to run. And I was kind of curious, like for unit test, that's pretty expensive. So how do you think about balancing like correctness versus cost, especially given that like with a theoretical kind of test pyramid, like unit tests should be at the bottom where it's cheapest, right? Quickest to run. If you're adding all these extra constraints to add more correctness, but also increasing the cost, how do you balance that?
That's a really good question, and I'm afraid I don't have a simple answer for that. Languages that are the actual theorem provers, which basically their compiler, their type system is a language in itself. They have this concept of inductive proofs, where the compiler can, by induction, by mathematical induction, prove your theory without having to run all the cases. It will check whether the way you run your system, if you have loops, whether or if you have recursion, is it always run on a structurally smaller value so that eventually you'll end up with some base case? So it's not running indefinitely, or it's not like growing. But this is limited to a very few languages that I don't think they're even like production or enterprise ready, so to say. So balancing this act of whether I write theories, general theories or tests is our job.
Got it.
And maybe, if I run it for just a list of 100 elements, it would probably take me, 10 milliseconds. And maybe that's enough to test for 100 elements. Maybe that gives you enough confidence. I just wanted to give you this ridiculously high number for the sake of an argument.
Cool. Just a quick follow-up to that is do you think about these types of tests also being are these types of strategies, I guess, that you mentioned being applicable to other types of tests higher up on the pyramid, like integration tests, functional tests, that kind of stuff? Or is this really just directed towards unit tests only?
I would not go that far as to say that we should write integration tests in that manner, because it might not be feasible. This is something worth exploring. I haven't never seen something like that in practice, only at the unit test level, really. And maybe there are ways to approach it in a more correctness or mathematical proof type of way. But I haven't met a case like that. If anyone did, please share.
Thank you.
Stress test. Yeah, that could be an example of something that you can actually prove. In fact, there is a concept that is called micro benchmarking, which is where you unit test your methods for performance, and so, for example, you can actually test whether your algorithm is actually O n log n complexity. So this is your theory. My algorithm that I wrote here is O n log n. Please run the test and tell me if I'm right. And that's treating whatever is inside as a black box. So potentially you could have a certain family of tests written in a similar way.
Hi, the question. You said that you should match values in test as possible. For example, I have 20 months in input. So what do you think about writing test without with random numbers? So each time test runs, it takes random number. What do you think about this? So it's like.
So actually, you need to be careful about using randomness in tests because you always want to trace back and you want your test to be deterministic. Having said that, you can always use randomness with the same seed so that you have deterministic randomness, and actually the quick theories tool that I presented here has this notion of random seed, because sometimes you just want to run a sample. So let's say I don't want to have two lists of 100,000, size of 100,000, and I don't want to test every single permutation of the two. I just want to test every 10th or every 100th, and I want the sampling to be random. It allows you to define a seed of this randomness, and you can then start using, random strings, random usernames, random lists, and so on and so forth. So you need to think of what value does introducing randomness bring. If we're talking about testing for general properties of your system, where you do not have time to execute all the cases, then you want randomness. So that if we are executing only a sample of cases, better be sure this sample is random. Otherwise, it will be biased and it will probably not be that high of a quality of testing. All right. So thank you very much. Thank you for attendance. And I was really delighted to be here.